astroparticle physics, there are two main subjects. One is dark matter and one is CMB and inflation. So these are the main two topics I'll cover. And in dark matter, well, dark matter, you probably all know that there is a form of matter which has not been identified. So it could be neutrinos, it could be something else. So I'll start with what we know about dark matter. So I'll take a few lectures about dark matter and then I'll switch over to inflation and CMB. So this is about So let me start with something which we know. If you have a solar system and you plot the velocity versus radius of all the planets, what you'll find is they'll fall in a regular line. Okay. And so this curve, so if you take Earth, the velocity is 30 kilometers per second and the radius is 1 AU. I'll tell you what is 1 AU, that's 1 astronomical unit. So this is a distance from Sun to Earth. Now this is a regular curve and the reason for that is everybody knows that you have this equation that the centrifugal force should be, or the centripetal force should be provided by gravity. So this is G M M. So here M is the mass of your planet and this capital M is the mass of the sun. Okay. So you can see that basically this tells you V is proportional to Em upon. So if you take this curve and you put in V equal to this much, 30 kilometers per second, AR for the Earth is 1 astronomical unit, and from here you can plug in these things and calculate M. So you try to do that and calculate the number just from this information. Okay. And astronomical unit is 1 AU. So it takes, what you can calculate it from is that it takes 8 minutes for light to travel from Sun to Earth. So having from this information on the board, you can calculate what is the mass of the Sun. And you can figure it out, and the answer is 10 to the 57 GeV. So here I will be using units where h cross is equal to c will be set to 1. So your masses, the unit of mass will be the unit of length inverse, the unit of time inverse. So some practice on these units, how to convert. So basically your mass will be GeV and the length will be GeV inverse and so on. So some practice of these units in the tutorials. Okay. So for instance, in these units, G is 1 upon m Planck square and so on. So you can, from this information, you can work out the mass of the Sun. Now the point of this exercise is that from how this is called the rotation curve, how the V changes with R can tell you, give you some information about the mass which is holding these something in orbit. So in this case, it's the Sun which is holding the planets in orbit. But there is a possibility that there is some dark object in some other situation. You don't see that object, but you see the stuff which is moving around. So using the same principle, one can figure out what is the mass of the unseen object. So this is what is seen in this rotation curve of galaxies. So here a galaxy has, let's say, a disk shape, and so there is a central bulge where you have a lot of stars. So there is a central bulge, and then there are some stars which are distributed in what's called a spiral shaped arc. So basically most of the matter is in the center. So if you now take the dust in the galaxy, or the known molecules in the galaxy, cyanogen and hydrogen, whose spectrum you know, and you look for, so this is done for galaxies which are outside the Milky Way, which are like edge on, you can measure the velocity of rotation of these galaxies. And velocity not for the whole galaxy, but the dust in the galaxy. Okay? So all the dust is going around, and by dust I mean basically molecules whose spectrum is known. And from the Doppler shift of those known spectrum, you can find out the velocity. So basically from this, you can find out VR upon R. And what you expect is like that, it should go down. Because you have something which is lots of stars in the center, and if there is dust moving around, then it should obey the same type of relations, which go as 1 by square root of R. What is seen actually is, so this is expected. What is seen actually is something like that. So this is the velocity as a function of radius. So this velocity is something like 220 kilometers per second. That's the number for the Milky Way. And where it turns is at what's called the 5 kiloparsec from the center. It changes behavior. And the sun is located somewhere here. This is the sun. And this is 8.5 kiloparsec from the center. So now you try to figure out. So it's clear that it is not this central density of stars which is holding the sun and the gas in orbit. Must be something else. Because if it was just this one, then your velocities would go down like that with this. So you have to find out. So the first question is, what is rho of r? Rho of r means that there is a, let's say there is a distributed mass. Okay? So this is a mass density. And what is the distribution of this mass density such that you get this velocity curve, such that v is equal to constant. So let's say we want a distribution which will explain this part of the curve. Okay? So what you do, so the equation to use is at, so let r be some radius here, r, and the total mass inside that r this is so this is the integral from 0 to r of this volume integral of the density, mass density, from 0 to r. So this would be the total mass enclosed in the radius r. And then this mass, then gmm upon r square. So this effect of this mass as far as gravity would be as if this whole thing was located in the center, just like the sun. So you have this equation again. The centripetal acceleration is provided by gravity. Is this so clear? Everybody? So what would be rho r prime? Yeah. Go, this whole thing. As a function of r, to give you V, which is a constant. So any guess? So this would be something proportional to 1 by r prime square. So you can put that in and see that if it is r prime 1 by r prime square, okay, that cancel with this r prime square, and so here you will get a r, right? So then this r and that r from there will cancel this r square, and you will get a v which is constant. So this will imply that v is a constant. So this was only if you go at a large distance. If you have so we already know from this curve, so it's a little short blackboard plus. At short distance, at r, let's say small compared to 5 kiloparsec. So this is called the core radius, RC, this point. So at short distances, you can see that v is not a constant. It goes something like v is proportional to r, goes linearly with r. And you want to find out what is the form of v. Now again in the same equation, what is so what distribution will give you v which is proportional to r? And again you can check that if you take rho r prime is equal to some constant at r smaller compared to rc. Okay. So if this was a constant, you can write down the same equation with this as a constant, take it out. Okay. So you will get basically and here you can again see that this will tell you that v is proportional to r. So you need a distribution which is at large distances it goes as 1 by r square, okay, and at small radii it goes as which is a constant. So one of the models which was, so people try to fit various distribution which will reproduce the observed galactic rotation curve. So this thing is called the galactic rotation curve. So the first example is rho r is rho c divided by 1 plus r upon rc square. Okay. So you can say this distribution has the property of what you need, that when r is small it is a constant, and when r is large compared to rc it goes as 1 upon r square. So if you have this kind of rotation curve, it will give you something like that. But that is a sort of a simple fit. But people try various fits, and the most popular called NFW, named after the authors Navarro, Frank, and White. And this distribution is often used is rho c r upon rc gamma something complicated. So there are several parameters. Gamma is a parameter close to, so its value is about 1, and this is the core radius, this is the core density. So one has several parameter models to fit this. And you can do this exercise that if you take this model, what is VR at R greater than R and R smaller than R. So take this model and take the two limits and you can work out what is how the velocity changes with R, and that's how the real Milky Way. So this is the Milky Way distribution. Distribution of what? Mass of what? Mass of something which is unknown, not the stars. So this is the dark matter.
Sir,
Yeah.
sir, at what point velocity would be constant? Like
What?
at what point, at what distance, velocity would be constant? Like at large distances.
Yeah. So velocity is roughly constant after the RC, which is 5 kiloparsec. So at the distance of the sun, which is 8.5 kiloparsec, and this goes all the way to 50 kiloparsec here, and more. 50 to 100 kiloparsec, it is supposed to be like that. But
why it is only dark matter? Because inside that there are stars also, they
Yeah.
have masses.
Yeah.
They have some contribution to the velocity of the stars.
yeah.
Why you are taking only the
So as I said, if you just first you take only the known matter, okay, and you will find that the known matter is totally concentrated in the center. It's very less in the, so only the galactic center is the most mass. So then that will behave just like the sun. So your velocity curve would be expected to be like this. And actual one is like that. Okay. So one postulates that there is some new form of matter which is distributed, which is holding the stars together and the gas is going around. What?
some subtraction from the sun, so we thought that observed then that expected. If that expected is subtracted from the then that
Okay, so you are making a good point that the total velocity curve would be the sum of this plus this one. Okay, so here, as I said, we said that this V is V should go as, so for V, which is at R is equal to at small distances, okay, rho should be rho C, right? So this is only if the dark matter is there, okay? But here you can see that when this is constructed, okay, when R is small, this is just gamma, right? And gamma is actually 1. So this is actually not a constant, because when they fitted it with the Milky Way, this fit says that rho dm, rho r dm plus rho r stars or luminous matter should explain the rotation curve. So in the center, it's the combination of the dark matter plus if you add the luminous matter, which should explain that constant. So then this is the fit for the dark matter part.
Sir, this gamma is a parameter in the NFW model.
Yeah.
What is its range?
Gamma is close to, as I have written here,
Gamma is close to 1.
1.
And
Most of the NFW is written with gamma equal to 1. So here you just write this and you write 2 here. That is the generic NFW. But small variations of NFW will have an arbitrary gamma.
okay. And this profile is only for dark matter distribution or all?
No, this is only dark matter. That's what I was explaining, that this is the dark matter distribution. In addition, if you take the luminous term, that will give you the actual galactic. So that example was assuming that luminous is negligible, only dark matter explains everything. So that was a sort of a toy model. But in real world, the luminous matter becomes important at small radius. At R less than RC, the luminous matter is also important. So then this is the fit.
Is that 2 minus gamma?
Hmm?
The power that
3 minus gamma. It's not 2 minus gamma. So it doesn't fit that actually. So that was only dark matter. So this is a significant deviation from that. Okay, so now the most important thing in all this galactic distribution is that by fitting all these parameters, and there are many other things. So what is the density of dark matter near the sun? Or near the sun means in the galactic scale in the solar system. So for instance on Earth, near sun. So this was worked out by in a paper by, so you can check this out, Catena and Julio. So if you type this in Google, this paper will come up. And so they fitted the rotation curve. They also took this, so if you have the, so this is the disk and the sun is here. The stars in the disk also have oscillatory motion in the vertical direction. And that motion is actually, it goes up and then it is brought back. The gravity which is responsible for that is also the same local density of the dark matter. Okay? So the rotation curve plus the oscillation of near the sun of the stars in the vertical direction all together tell you what is the density of the dark matter near the sun. So that actually is, so this is called that. So this is something like 0.3 to 0.4 GeV upon centimeter cube. So basically, if you see that the proton mass is how many GeV? Nearly 1 GeV. So there is a 1/3 of a proton per cubic centimeter in dark matter everywhere. Okay. So this is a very important number in the sense that when you are looking for direct detection of dark matter, so there are experiments which I'll talk about, that the dark matter is scattering some target which you set up in the lab. So you want to know what is the cross section and the mass of this dark matter. So what is needed is an input about what is the expected density. So the expected density is this much. So that goes as an input when you're trying to extract from the experiment the mass and the cross section of dark matter when you're scattering. And I'll come to that. Okay, so I'll move from the galactic dark matter to dark matter at a larger distance, the cosmological scale. So before that, let me discuss one point, which is, are neutrinos the dark matter in the galaxy?
Sir, you used 2 examples.
Yes.
The first one fitted that, right?
The first one is a toy example which tells you if there is nothing else, what would be the total distribution. Okay, the second example tells you that if you have the luminous matter distribution, added to that will give you then the correct rotation curve.
So this is only the dark matter?
Only the dark matter, yes. So I should actually write. So I said rho dm plus rho r gives you the rotation.
Sir?
So this example where I said find out this would give you that if this was just the thing, you will not get a linear relation here and a r equal to constant there, which shows that basically this exercise will tell you that including the luminous matter is also important for this. And so that was the contribution of this analysis.
Sir?
Yeah.
Why are you not taking the one distribution then?
The what distribution?
The distribution number 1. we had
This was actually there. See, that was a very old fit. Okay. So it has been progressively getting better. So this is the old one.
So why are we not taking this and assuming a dark matter?
So in this fit, they only tried to fit the dark matter to the rotation curve. Then what was seen was that actually, as the more telescopes came, they saw more and more stars in the galactic center and around the galactic center. So the visible matter profile now is much more compared to what was expected at that time. So this was, I think, in the 80s when this was done. So this takes into account the contribution of the visible matter also. So this was as if this was the only matter. So this assumed the dark matter is the only dominant matter.
But sir, you were saying that the NFW model is for dark matter also. And
The NFW matter, this distribution is a dark matter. And I said if you add this to the visible matter, then that will give you the total rotation. Okay, so
neither gives you the correct curve. Neither one gives you the correct curve though. So to add them both.
So dark matter is, as the name suggests, it's not luminous, which means that it is not visible in your optical telescopes or any radio telescopes or any of the telescopes which measure photons. So that tells you that dark matter, so what would be the property of an elementary particle if it should not interact with photons?
Neutrino? Chargeless.
Chargeless. That's right. So if the particle does not have a charge, then it cannot interact with photons. So in standard model, one of the candidates is neutrinos, which does not have a charge. So the first thing one can check is whether neutrinos can be galactic dark matter. So neutrinos with a mass. So can neutrinos mass be galactic dark matter? So the first thing is that neutrinos, it is known that they are very light. There are various experiments. So if you, and this is a very large density that you want to fit, 0.3 GeV per centimeter cube. And neutrino masses are expected to be in the EV range, which I'll tell you why. So they are not heavier than an electron volt. So to fit this large density, what you need is that the neutrino should be as densely packed. The number density should be as large as possible. But neutrinos, as you know, are fermions. So there is a limit to how many fermions you can concentrate together because of the exclusion principle. So if you take the exclusion principle limit, that you fit in as many neutrinos per unit volume as possible as allowed by the exclusion principle, so then that tells you that your distribution function and you will hear more about distribution functions in the tutorial. So this would be, I hope you have seen some distribution function. This is one for, so this distribution as a function of p is 1 and till some pm, and it is 0 after that. Momentum. Distribution in momentum. So this is what is called the degenerate limit, that you are packing in a, so there is one fermion for each momentum state and 0 outside. If it is a boson, then the closest packing would be all the bosons can have momentum 0. That's the Bose condensate. That's called the Bose condensate. But that condensate is not possible for fermions because each momentum state has occupancy 1. So you will hear more about distributions later in the afternoon. So this is 1 for P less than Pf, and this is 0 for P greater than Pf. So that's the what I've drawn here. Now the number distribution, number density is okay, and so this GI so is the spin of, so this is the distribution for spin up, is the identical distribution for spin down. Okay, so there are two spin states of the neutrino, and if you take both together, you have put in this degeneracy factor, this factor G, which is the number of states, independent states. So this is 2 for each new species. So there are 3 species of neutrino, nu E, nu mu, nu tau. For each neutrino species, there is spin up and spin down. So I am calculating this for each neutrino species. Okay. So if you do this integral, and for the experts, why this has this 1 upon 2 pi cube, the answer is, are you laughing? Why is there a 1 by 2 pi cube?
Rajit was asking me yesterday.
Why? Okay, so the expert, so that's why I said for the expert, I didn't know he was asking you though. So, the distribution function tells you what is the, it is 1 particle per unit momentum per h, per h. Okay, and we are using the unit h cross is equal to 1, where is h upon 2 pi. So to go from the h, one momentum this thing per h cube to one this thing in h bar cube, which is 1, you have to put in this factor of 2 pi. So this is only for the experts. And okay, so this is because we are using the unit h cross is 1. If you take the unit h is 1, then this 2 pi cube will not do. Okay, but anyway, so this is the distribution function, and here you can see if you use that distribution, this should be equal to GI 4 pi by 3 PF cube, and PF would be the maximum momentum which is there in this distribution, and the momentum for a non-relativistic, so neutrinos, if they are in the galaxy, they have to be non-relativistic. So the momentum should be m nu times the velocity of the neutrinos, and this tells you that this is V cube. Because if it is relativistic, then you cannot confine it. Okay, so to confine it in a gravitational potential, it has to have a be non-relativistic. If it is relativistic, then you can confine it, but it goes to a very large, the distance of confinement. As you know, if it was massless, it cannot be confined. So similarly, if it is its mass is very small compared to its energy, then it's called free streaming. So I'll explain it later. But so the free streaming length of a non-relativistic particle is much larger than the galaxy. You cannot confine it in the galaxy. So it has to be non-relativistic. So this is the relation. So this tells you what is the number density.
2 pi cube was there, right?
Huh?
Numerical factor. 2 pi cube.
Yeah, 6 pi square. Yes. So there was this will be 6 pi square. So 2 pi cube from below and 4 pi from the top will give you.
Sir,
Yeah.
so what is a non-relativistic neutrino?
What is a non-relativistic neutrino?
Yes.
Okay, so a neutrino right now has a temperature which is something like your photon temperature. I'll just tell you the exact relation today. Okay, and the photon temperature is 10 to the minus is 2.75 degrees Kelvin, which is 10 to the minus 4 electron volt.
Okay.
Okay. So if the neutrino mass is an electron volt, then its mass is larger than its temperature. That means basically its mass is larger than its kinetic energy. Okay. So the neutrino now, if it has a 1 electron volt or 1.1 electron volt, anything larger than 10 to the minus 4 electron volt is a non-relativistic particle. So its mass is larger than, neutrino mass larger is larger than the neutrino temperature. If that is true.
If that is true.
If that is true. So we do not know if that is true or not. So there are 3 species of neutrino. We know one neutrino has to be 0.05 eV from the solar neutrino experiment. But we do not know the other neutrino masses. So it is possible that some neutrinos are relativistic. But at least if one neutrino is non-relativistic, then this can act as a dark matter. That is the assumption, that if you have one non-relativistic neutrino.
But aren't the masses constrained by the mixing angles typically?
So what the oscillation experiments tell you is exactly what they tell you is there are 3 masses.
Yes.
Okay, and these mass differences. So delta M solar, it is 10 to the minus 7 eV square, and delta M square atmospheric is 10 to the minus 3 eV square. So this is coming from the solar neutrino oscillations, this is from the atmospheric neutrino oscillations. But these are 3 neutrinos and this is 0. Okay, this is M1, M2, M3. So what is known is the difference in the neutrino masses. What is not known is the absolute neutrino mass from 0. So if this scale is something like 1 electron volt,
Okay.
then the neutrinos, in addition to these oscillations, would also provide cosmological dark matter. So that is the assumption behind this. And that it's not known right now what exactly is the absolute neutrino mass.
But from a gravitational if you have a curve background, you can actually talk about absolute values. Is
Yes.
that the idea?
In the curved space or for cosmology, the absolute mass is the relevant quantity.
Okay.
So that's why I'm putting the absolute mass there.
Okay.
Sir, so
Yeah.
dark matter has been formed at a very early stage of the universe.
Yes.
So the temperature was very high then.
Yeah.
So how can it be non-relativistic?
I'll discuss the whole thing in next 2 lectures. So basically when the dark matter, when the temperature goes down, okay, when it falls, the temperature falls below the mass of the dark matter, then the dark matter becomes non-relativistic. So even in the early universe, all particles are relativistic. But as the temperature came down, if those particles survived, they are all non-relativistic now. Okay, so that details of that is what I am doing now, today and tomorrow. Okay, so I was here. This is the number density of dark matter in neutrinos. Now the rho is m nu times n for non-relativistic particles. So you have the number density, and number density times the mass is the energy density. So this is the energy density. This is the mass density. So you take that formula, put m nu equal there, so you'll get a m nu to the 4 there for the rho. Okay. Now you take, I'll give you. Okay, so now you take the numbers. Rho is equal to, so you know that your galactic density is something like at the solar system it's 0.1. So you take some number which is, okay, any number which is close, GeV per centimeter cube. You can take 0.3 or 0.4 or whatever, some number close to that. So this is a reference number that this is the density of dark matter. the velocity is 220 kilometers per second. So why is it 220 kilometers per second? We're talking about the velocity of the neutrino now, because we have to put that in that equation. So the velocity of, as I said, the velocity is the velocity which is measured of the luminous matter. But it's the same formula for any mass. Yes, we see in that mv square upon r that the mass of the particle which is going around cancelled out. So any particle, whether it's luminous matter or dark matter, shares the same velocity. Okay. So you take the same velocity. Now put in these numbers here. So rho, put rho here, put v there, take g equal to 2, and what you will get is that m nu. So if you put these numbers, what you will get is m nu is 21 electron volt. So this mass is expressed, this is called what's called Gunn-Riemann limit. This mass would be m nu should be greater than 21 electron volt. So if you look up a book, this numbers will be different because it will depend upon which galaxy you are fitting. So if you have a dwarf galaxy, it's a different number. Milky Way, it's a different number. So this number comes from the numbers I put here. For the velocity and the density, this can change from galaxy to galaxy. So this is not an absolute number here.
So we have to consider all the three species, right? Not just one.
Yeah, you consider all the three species, that's correct. So one should actually take G equal to 6 here. Yeah, but this number was yeah, so this number was G equal to 1.
That is somewhat understandable.
So one should take what
There will be some degeneracy factor, essentially.
so G should be 2 times 6 to have all the neutrinos in there. And then what does this number be? Okay, you have to work that out. That m to the 4 times G was giving you this when I took m to be 2. So you can work this out.
So why 2 times 6?
2 times 3. Yeah, you can actually work this out. So this was for one neutrino species. So this is the number which is there for, so 21, I'll keep this number. If you have one neutrino species which is non-relativistic, you can take this number, but if you have 6, you can work it out. Is that clear? What numbers I'm putting? So this number, and why did I put, so here up till here I had equality. Why did I finally put mu is greater than 21?
I don't get it. I don't know.
Because I was, all along
Non-relativistic, that's why.
calculating the number density is equal to that, then rho is equal to that, and this number, when I put equal to 1 g per centimeter cube,
That's the number.
I get a number which tells me mu is equal to 21 eV. So why do I say that real world mu should be greater than 21?
You can have relativistic corrections.
No.
Like, critical, this calculation is done in critical.
I don't understand.
Actually, rho, I mean, you calculate it at the core, outside core, it will decrease.
Okay, so not real. We were assuming the maximum pack limit, the degeneracy limit, which means this one. In actual, this thing, the distribution is something like that.
Okay.
Okay. If it's not exactly degenerate. So if it's not exactly degenerate, then the density is small, then the mass has to be larger to give you the same rho. So we calculated for the maximum degeneracy, which means we calculated the minimum mass which will give you the rho. Okay. So this is the degenerate stacking. It's called the degenerate stacking or and this is actual distribution. This is generated distribution. When do I have to stop? Huh?
Exact.
15.
Quarter
Quarter past 11.
Let me check.
Huh?
I think quarter past 11, if I remember correctly.
Okay, I think I can. Huh? Okay, so
Now it spreads out.
I have one more topic to cover and
Under the curve is the same.
sure. Okay, so now I'll go from the. So the idea is that this is actually not possible because I'll now calculate from cosmology what is the expected neutrino mass, and the neutrino mass will be less than an electron volt. I'll show you. So this is tells you this is a contradiction between what is needed to pack your galaxy to give you the rotation curve and what you get from cosmology.
Or some G1.
Okay, so the conclusion from this calculation is that neutrinos are not,
11:30.
11:30 I can finish. Oh, then that's good. I can finish. Okay. So now I'll go to this cosmological scales. So this is something like 1000 megaparsec. So what is a parsec again, you ask in the tutorial in terms of light years and so on. Okay, so cosmological scale is 1000 megaparsec. So at that scale, what is the distribution of dark matter, or is there a dark matter? So there is a dark matter, and it's measured through the CMB, the microwave background. So what is the calculated number? That's what I'm going to calculate now. So supposing there is some particle species X that can annihilate, okay, when it's thermal equilibrium of the particles, it can give you photons, it can give you E plus E minus,
Sir,
nu bar, yeah.
what do you mean by cosmological scale?
Cosmological scale, see the scale of the galaxy is 100 kiloparsec. Okay. 1 parsec is 3 light years, 3.1 light years. So the galaxy is 100 kiloparsec. Then there is a cluster of galaxies which are a few megaparsec. You mean 2-3 megaparsec. Then if you go to 1000 megaparsec, that is the longest distance you can see from the beginning of when the universe was created to now. The light could have traveled only from 1000 megaparsec. So that is called the cosmological horizon. So that's the cosmological distance. So if you have annihilations, at all points you have annihilations which create photons, and then the back reaction takes place, the photons give you this dark matter, I call it X, and they can be neutrinos. I mean, at the cosmological scales, dark matter can be neutrinos, if not in the galactic scale. So, at equilibrium, supposing something is in thermal equilibrium and it's relativistic, so where temperature is large compared to the mass, then its number density is this Gi, the number of spin states, times 1.2 upon pi square T cube. And this is for if they are bosons, and factor of 3/4 times the same number if they are fermions. So fermions, because of the exclusion principle, they are a little less densely packed compared to bosons. And these numbers you'll see from first principles. derived in the afternoon. So this is if T is large compared to M. Supposing the mass, so there is some temperature at which your particles are going this way and then these particles are relating, giving you back that. Okay? And if the temperature is large compared to the mass of this particle, then this is the number density. And this will be the number density of all the particles with the different multiplicity here. If the particles are non-relativistic, that is T, so at some point the temperature goes below the mass of this particle, that is this. So this mass is the mass of this particle we are discussing. So if the temperature goes below the mass of this particle, then the number distribution, which is at thermal equilibrium, is now that's called the Boltzmann distribution. Again, they all come from one formula and different limits of calculating that, and you'll cover that. So again you'll see this in the afternoon. So these are basic thermodynamic relations which I use. So what this tells you is that when T goes to 0 compared to the mass, when M upon T goes to 0, infinity, that is T goes to 0, okay, and equilibrium goes to 0. So they exponentially go down when the temperature goes down below their mass. So if particles are interacting and they remain interacting, they will disappear. So what will happen is that as the temperature goes down, more and more light particles will be generated. So all the equation will be one way, not the other way. So there will be exponential depletion. At some point the particles will become 0. So you should not expect any particles to be non-relativistic if they were always in equilibrium, there was a thermal equilibrium. So the only way to break this, to get some non-relativistic particles in the present epoch, is that they should stop interacting. The interaction should be ineffective, so that they do not annihilate and become lighter particles. So this is a calculation that I will do in detail now to tell you. So this is called decoupling. So I will just write down this. So the only way for particles to survive to the present epoch is decoupling. And I will now tell you what exactly is decoupling. So let me first write the metric which is of the expanding universe. So this is a square t dx square or dx dot dx. So you must have seen this where I put c equal to 1 again. So this is what is called the FRW metric. And you must have seen in special relativity, this ds square is dt square minus dx square, no a. But if you have an expanding universe, then the space part gets multiplied by a factor a. So that is called the scale factor. So your physical distance dx physical is basically a times a of t times dx, which is the coordinate distance. So this dx, the coordinate distance is also called the co-movement. This is fixed. So your physical distance actually, if you have a box of 1 meter cube, in time it will grow 2 meter and so on as the universe expands. So, and this how this A changes with time. This comes from Einstein's equation, which I'll cover later. But right now the point I want to make is that the volume of any confined number of particles, the volume always grows as a cube times some v0. Okay. So if you have v0, the volume which is, so I should write it like at some time, then with time where there is a, maybe I should write this as correct. So the actual volume will grow if the scale factor changes of any fixed volume. Yeah.
How is temperature defined?
Temperature is, you can define it through the average energy. So one can calculate the energy for a distribution, and the temperature depends upon the energy. Sorry, the energy. So energy is something like 2 times temperature, 2.1 times temperature for bosons, and 3 point something for fermions. So temperature is the measure of average kinetic energy. No, V is some simple volumes. Any, so there is a, let's say you take a distribution of gas at some point A1. Okay. So there is a distribution of gas. So if nothing else happens, this gas will expand to, so this is V, which is proportional to V1 will be proportional to A1, and V2 should be proportional to A2. So then does this, is the correct relation? Yeah. Right? So any distribution of gas left alone without any box, any confinement agent, just because the space expands, the gas will dilute.
So it is after some time, right?
After some time, yeah. So this is a cosmological, this time is a cosmological time. But in the early universe it is actually not a very long time. It's a microscopic time. But in the present universe, if you want to see the change, it has to be, the time is the cosmological time, some billion light years. So any volume will expand like that, just because space expands. Now, if suppose you have a non-interacting particle, so there was no non-interacting particles, the number density n, which is, so this is the number density, so this is number per volume, will go down as a to the power minus 3. So the number is conserved, they are not interacting, okay, and the volume is going as a cube. Okay. So this tells you that if you have a cube times n, the d by dt of that is 0. Because n is proportional to a cube, so if you multiply a cube times n, then this n is a constant. Okay. So n is basically increasing because of this volume factor below. So if you multiply a cube, which will cancel the increase in the volume, there is no change in n. Okay. Now the same equation you can write it as 1 upon a cube times that is also 0. So this equation, which you expand, this is n dot plus 3 a dot by a n is equal to 0.
What equation is that?
So this is often written as n dot plus 3 h n. So this is for non-interacting particles. So where the number is not changing. Just
And also it should be non-relativistic.
what?
Non-relativistic.
No, this is for both relativistic and non-relativistic.
I don't get that. N is proportional to 8.
Yeah.
Again, you are effectively assuming that as space expands, there is no creation of particle.
Correct.
So why is that assumption true? Even for standard cosmological expansion, there are particles created.
Well, there are two ways of particle creation. One is through a metric, so something like your Hawking radiation. The other is through the particle physics interaction. Now, the Hawking radiation is actually a gravitational process, a very weak process. So it does not play a role other than maybe in the early universe or in black holes. But in the real universe, it's the interactions between different particles, what I have written there, XX going to gamma gamma and so on. Those will be the more effective in changing the number of particles. Okay. So here I am assuming that Hawking radiation type of process is not there. Okay. The gravitationally created particles are not there. Plus, there is also no interaction. So this is just an assumption. So now I'll tell you how to correct this if there is interaction. Okay. So when there is no interaction, then for both relativistic and non-relativistic particles, this is the number density, and dot is d by dt.
So what do you mean by interaction here? I'm not quite following.
Interaction means that you have basically E plus E minus.
Okay.
Give you gamma gamma.
Okay.
So this is an interaction.
Okay.
So basically, if this interaction is allowed, then E plus E minus, when the temperature falls below their mass, will all become photons.
Yeah.
But supposing you assume that this interaction is not there, or it is ineffective, and I'll tell you what it means to say that something is ineffective.
But then this is a non-relativistic point, right? I mean, if it's relativistic, you have to allow for this process to happen.
If it's relativistic, no, it need not also happen. It depends upon the strength of the interaction. So that is the point. It's nothing to do with relativistic or non-relativistic. In relativistic, your number density of this x, if this process is taking place, will be like that. If non-relativistic process, it will be like that. But sometimes the strength of the interaction is weak compared to the expansion rate. So that is what is the idea of decoupling that I am trying to get at. So let us assume for the moment that there is no interaction. What happens? So I will put now the actual world, in the real world, what happens if there is an interaction. Okay. So with no interaction, your number density does not change. And it only changes because of the expansion. So that is the point. So this is the change. If there was no expansion, this n dot would be 0. With expansion, this is the thing. Now we put in interactions. So there is one more term on the right hand side.
E is for displacement, right? So charge density is small.
So what happens with interactions now? With interactions means you now allow process like E plus E minus, gamma gamma, etc. Then this equation 1 by a cube d by dt a cube times n. The right hand side will not be 0, but it will depend upon what is called the cross section of the interaction times n square minus n equilibrium square. So the reason you have this type of thing is that when n becomes larger than n equilibrium, so there is an equilibrium number. When n is larger than n equilibrium, then you will have equations which the equation tells you that the number density will change to decrease the number. So that the equation proceeds this way. So when n greater than n equilibrium, so n is, I am talking about the n of this, n is number density of this x particle. So when n is larger than n equilibrium, then n dot is small, is negative. Basically, it means that the equation will proceed this way. So xx will actually go this way, and n dot is less than 0. And when n is smaller compared to the equilibrium number, then the equation will proceed the other way, faster, and n dot will be greater than 0. So the number of particles will grow. So this equation tells you basically that it will be driven to the equilibrium number. Okay. So this is what's called the Boltzmann equation.
So how do you get this equation?
Oh. This is, well, depends upon where you want to start. So where do you want to start? From field theory or statistical mechanics, or there are different types of derivation of this equation. So,
but all of them assume equilibrium physics, which I'm not able to see actually.
this is not actually equilibrium physics. This is non-equilibrium in the sense that there is a equilibrium number, but the actual process is not in equilibrium, it is going towards equilibrium. So that is the point, that this is the number which n would be if it was an equilibrium.
Okay.
But n is some number which is different from equilibrium.
So, but how is it deduced? How do we know what that number is?
Well, so that number is by solving this equation.
Okay.
I'll give you an example that you solve this equation to get n. And then somebody asked me, how do you derive this equation? So that again, the derivations I have seen is basically that you use that logic to have the left hand side, and then for the collision term, you calculate the change in number in your scattering cross section. So this is nicely explained in this Doddleson. There is a book called, but the derivation is sort of intricate. So I have not derived the,
How will you get, what motivates you to get this average over sigma v? And what is quantity?
Okay, so I'll explain sigma v. So let me just finish that. This can be derived from field theory, the right hand side. So this is actually what is called the cross section, the collision cross section. So one takes the left hand side and say if there is no interaction, that is 0. If you have an interaction, then put in the interaction rate at some finite temperature. Okay. So, but it's not a difficult calculation, but it's a long calculation. But if you are curious, you can read this. It's a book by Doddleson about cosmology, and you can see this. But as I said, there may be different derivations of this. So the one I know is sort of like the field theory motivated, but there could be a different type of derivation from statistical mechanics and so on. So,
Sir,
Yeah.
I have seen this Doddleson. It is quite difficult to find out this equation. So if you can do, it would be helpful.
yeah, I can do it. I mean, this is it's not a difficult, this thing is actually I do this when I teach, a long course, so I can do that. if
it
most,
would be helpful for us.
okay, so I can actually, maybe we can do that at some point, yes. So yeah, tomorrow I can give you the derivation of this. So it's actually not it's not a difficult equation, it's just a tedious equation, but yeah, maybe I should do it. It's interesting. So since you are curious, I can do it. Okay, so let us assume that this equation exists, which I'll prove tomorrow, okay, from the first principles. But now, okay, somebody asked me what is sigma V. Now, sigma V is the cross section. So again, I hope this is again one of the things you are expected to know, but probably have not studied. So this is from any interaction, like that picture I drew, there is a cross section which tells you what is the rate at which this interaction proceeds. Okay, so the relevant, so one calculates from those diagrams a cross section. Okay, what this is, that this cross section assumes some particular energy, that if you have energy of an incoming particle, you will get a number for the cross section. That this tells you what is the cross section at a given temperature. So what is called the thermal average. So thermal average is a distribution over different energies, and that tells you for a particular temperature there is some peak energy. Okay, so this thermal average tells you what is the peak energy for a given temperature at which this cross section should be calculated. So how many of you have never seen a cross section?
This V was a subscript.
No. Sigma is the cross section. Sigma V is the interaction.
No, n actually the interaction rate I would call n times sigma V. So sigma V is your cross section usually. V is 1 for your high energy, so we don't write that. But if you have non-relativistic particle, then sigma V would be the
cross section.
No, sigma is the one which you calculate from the diagram, right? Not sigma V.
The diagram actually gives you sigma V.
So the left hand side is the rate
What?
with respect to time. So the left hand side is rate.
For non-relativistic, it is sigma.
Then there is a dt at left hand.
Yeah.
So there should be a time inverse in that.
Non-relativistic
And the
dimensionally.
d is basically
For
if I
relativistic,
take as velocity.
Yeah, I'll tell you what.
Actually, sir,
So
in
non-relativistically
the
it's
expression
sigma
of
V,
there is 1 by
dimensionally it's
V.
required.
What?
In
So
the
for-
expression of sigma, there is 1 by V. Sigma equal to 1 by V
We did this
and
last
some
time.
factor.
Mm-hmm.
So calculating that, we then again calculate the thermal average
Last
sigma
time.
V.
No, she is saying that what you automatically get when you calculate the cross section.
I think sigma V.
You get sigma V as per what I.
So for non-relativistic physics, it's actually sigma V, and relativistic it's sigma, and we actually covered this in last year's Circ school. So
Yeah, basically V is 1 in relativistic this thing, so we don't write it.
that's it.
But it is always sigma V.
Yeah.
That is the point. Okay. So if you do actually a calculation, you will automatically get a sigma V.
No, sir, but not thermal average.
Not thermal average. Thermal average is something else.
Yes.
Yeah. So what you get now, okay, I'll write one more quantity which is relevant. This is called the interaction rate. Interaction rate. Okay. This is sigma V times the n square. Okay. And if you work out the unit, so sigma V is area. Okay. Or so this is written as cm square or cm cube per second. Either of them is the area, sigma V. Okay. And this will be, if you multiply the number density cube, this will be, what would be the units of this? What? Per second. Second inverse. Okay.
Could you please repeat how do you have written interaction rate?
So the interaction rate is defined as the number density of the initial particles square times the cross section of their interaction. Okay, and the units I am saying, if you work out the units, that this is centimeter square or centimeter cube per second, let's take this one, then this will be just second inverse, right? So this is interaction rate is the rate at which the number is changing. Okay. So why we want to bring it in this form is, let's write this equation in this form where I write n dot plus 3h n is equal to gamma n times 1 minus, I think I made a mistake, n square, n equilibrium square. If I want to define, sorry, with this, no? Yeah, very sorry. This is centimeter cube per second multiplied by 1 upon centimeter cube. That should give you per second. So sorry, this is the interaction rate. Okay. So what have I done here? From coming from here to here, I taken out the n square. I written n square. Yes. I taken out the n square. Okay. Combine one n with the sigma v. Write gamma. Keep the other n as it is, and so this n square, when I take out, this goes in the denominator. Okay. Now this equation tells you something. Okay. You have two terms which are proportional, so you have a 3h n term and you have a gamma n times 1 term. Okay. This equation tells you that supposing gamma n is less than h times n, or 3h n. Is okay. At some point the temperature goes down, sigma v goes down, and the number density goes down in such a way that the right hand side, this number, which basically depends on the cross section and the number density, falls below that. Then basically tells you that again the right hand side becomes ineffective. Right? So then the RHS is ineffective. What does that mean basically? That the number density equation would again be back to n dot plus 3h n equal to 0. Okay? Yeah.
That equation 1 by aq ddt aq dot a, that equation is that the dimension is not matching in right side and left side, because n is dimension semi-cube and sigma v, that is semi-cube per second, and then n square.
A has, don't take any, so A dimension cancels here.
Yeah.
It is n divided by t.
Yeah.
Okay? Here h has a dimension of 1 by t because A dot upon A.
No,
Yeah, this also, you see, this gamma has a dimension of 1 by second, 1 by t, and n divided by t.
I'm taking that equation, that left side and right side.
No, it is matching. It should match.
The sigma v, that is semi-cube per second.
Yeah.
So the n square, that will have semi 6.
Yeah.
So that will be semi 9.
One is
minus 6.
Which one is that? N is, this is centimeter to minus 3 per centimeter. N is centimeter to minus 3. So it should match because you can. So N is N per V, it is centimeter to the minus 3. So please keep checking, that's good. Okay. So what was I saying here, that when this gamma n becomes less than that this side, then this becomes 0. So this is what is called the decoupling. Don't mind. Maybe I should do this. Okay. So, this idea of decoupling is that if your interaction, there is interaction taking place always, but if your interaction rate, which is given by this, sigma v times n for a quantity is less than the Hubble expansion, so what is the decoupling criterion motivated by that is the following, that so this decoupling condition is that HTD. So there is some temperature at which the H is proportional, is equal to gamma. So at some point, if these two are equal, and then after that, and at T less than TD, then gamma T is less than. So then that is what is called decoupling. That even though the interactions are taking place, but they become too feeble, so the only change in the number density is because of the expansion at that point. So I think I should. Okay, I will close right now.
Gamma is a function.
So yeah.
Is 1 by gamma the time scale at which the system equilibrates?
Well, I'm not. It will also depend upon.
Yes.
Yes, so yeah, that's true. It has a number density. Yeah, then that should be yes. So it will depend upon the cross section and the number density. So gamma is that. So 1 by gamma will be the time scale of equilibrium.
So at the decoupling condition, both the processes,
Yeah.
I mean reverse and forward, freedom.
Yes. So at the decoupling, both the processes reverse and forward will freeze out. So freeze out means that the time scale, like you are saying, the time scale of interaction is longer than the time scale of expansion. So the expansion is the more dominant process. So I think I'll stop here. So there are two types of things which I wanted to do. One is called the hot dark matter. Example is a neutrino, and then there is a cold dark matter. So whether it's a hot or a dark cold will be if your mass is smaller than the decoupling temperature, then it's called the hot dark matter. Okay. And if the mass is larger than T. So when it is decoupling, if a particle is relativistic, that's called the hot dark matter. And when it is decoupling and it's non-relativistic, it's called the cold dark matter. And the calculation of what is the present density of a particle depends upon whether it is hot or cold. Okay. So I will do these two things tomorrow. I'll stop here.